for okay. So again, from Kepler's equations, I think that is equation 10. If I'm right, delta nu times delta t. So time of flight is delta t. And equal to this. When t and r0 and v0 are given. So now we know xt. We want to solve for x, and here again s and c are individual functions of z, and in turn they are in function of x. So basically here on the right hand side is highly coupled nonlinear hyperfunction of x. Okay, so by all means, here there's no way we can solve for by hand. So here the numerical approach is this. We define, again, using the Newton's method. Newton method in generic form is this. Our next guessed value will be based upon the previous value, and by certain improvement is doing this. Let me write it up, that equations. Okay, so that is the format for Newton's method. And to fit into here, let me define what is f. F is a certain the functions we're going to solve. So by doing that one, we simply define. In Newton's method, we define this one basically is f. It's defined by simply is make the whole things one side equal to 0. So here, let me do this one. I divide, for the first equations, I divide the both hand sides by square mu, and then I move delta t to the other side. So here, let me do this one here. So here, this one is what that means. Let me box this one. So that is the box is going to here. Okay. So that will be a little bit clear, and divide by delta t. So basically here for this example is this given delta t. We find the root okay. So basically this is the root finding problems. The f of t equal to 0. When this function equal to 0, basically that means we have the solutions for x. Okay. And Newton's method for this one basically is based upon this format. So we have rewrite this one. And so basically once we have this, and let me just plug in the information for our function here. So that one basically is this. Right now I want to introduce these functions by this. So basically that one equal to again, for easy writing, I don't want to write the whole thing, so why not let me define this is as a t, as a function of x. Okay, I simply define this as a t, and that is the term used in our textbook. So basically that is the Tn. So fxn based upon this definition is t by the function at that one and minus delta t. Okay, and this one is basically become dt, dx, and x at xn. Okay, good enough? Good. And in our textbook, simply, they simply using the minus plus, basically that one is, let me write in our textbook, the expressions, textbook using these patterns. Okay, this equation is in our textbook 4.415. Okay, textbook adopt this positive sign, so basically they take the minus and get into this one. Okay, either way. So that is this, and furthermore, we have to manually calculate what is the dt dx. So here, let me make a note here. So derivative of this function respect to x, and we have to do that manually, and that one, I do it here. So that one basically is 1 over nu. So right now we just get everything prepared for programming. Okay, and if you look at the information in the bracket carefully, respect to r, actually this one is equal to mu over r. We have two functions, we have two equations. The first equation is about r. If you compare to that equation about r, that is exactly here. So basically derivative can be expressed to as r, and r is a function of x. Let me emphasize that's a function of x. Okay. So again, this is the r function. When we talk about the the universal formulation, we have two equations, and the first equation is about r. Is that equation? If you can have your lecture notes or on the handouts, that first equation here, I would say borrow yours. In this handouts, the first equation that is r. Okay. Okay, so right now we have everything ready, and then we see. So what we need to, I think I need to save all the things, but here I want to give you a little bit more the informations. So here these provide us the iterations. So our iteration is based upon this. Okay, so and we need to iterate. The iteration must start with certain initial guess. Initial guess is the major disadvantage of Newton search method, because if you make a poor guess, then sometimes you won't get the answers. Okay. So and a good initial guess will be the good exercise. So here I can have. My goodness, that is a long right hand. Do I have? We have this one. Okay. What is the best way? Okay. Utilize this one more time. because on my lecture notes I dispatch and I reorder it. Okay, so in the stack, the second page, the universal variables. In this page, sorry, bear with me for this kind of weird sign. In this page, I simply summarize the our result here. Again, that is the R equations I mentioned, and that is the delta T, the time of flight equations. And here we introduce the Z, and basically this page is a summary page of the equations. And in particular here we have the definition of C. C is defined as this one, and S is defined as that one. Okay, we can move on to the next page. So Sarah, you can look for the slides. So here again, above this one is the summaries of the equations we need. And starting from here, and this is the writing, this block basically is the writing we have done here. Okay, so for iterations, here we, again, this is the same patterns of the formulas we're writing here. So you can ignore the things above if you catch up all the information from the writing here. So that is the iterations. And we have this iteration scheme like this. And we have to meet certain criteria. If not, then we iterate. But the things must be start with the initial guess n equal to 1. Okay, so the remaining things is we are lacking is how to make a good guess. And that is in the next page of the slide. I think this is much better. So here for making the initial guess, again, you have to have certain knowledge about the type of the orbit you are working on. So initial guess for the making the search is this. For elliptic orbit, we make this one. For hyperbolic orbit, and this is the equation suggested by our textbook and very long writing. But here I simply copy it and to here. And for parabolic orbit, here is my suggestions, and seems it's not good. The suggestion is this: for parabolic equations, this is the equation corresponding to parabolic. And this one basically is a simple the polynomial function of degree 3. So basically we can easily draw a curve and to guess the root. I won't recommend this because this is a very old. A good approach is this. If you like for parabolic, you can also adopt this value. That would be easier. Okay, so if you like, and you can make the note, this is for elliptic and for parabolic orbit. This value is an initial guess for both elliptic and parabolic orbits. So with this initial guess, and we put it into iterations, and for each iteration we check against the tolerance, and then once we solve for x, then again we put into this formula. So the 3 again they show up one more time, and for those, okay. So that is the whole process, and let me try to implement the equation. So before we doing the remaining time, and I'm going to open up a blank the MATLAB sheet, and we start from scratch. And probably is everyone can work with me and see the kind of the trial and error.